Hi, my name is Giovanni D'Ambrosio, and today I'll be discussing the dynamic response of auxetic materials for blast protection applications, with the focus on the development and validation of a human skull model. Helmets have existed for decades, yet their basic design has not varied much. Most designs include a tough outer shell, an energy-absorptive inner liner, and comfort pads on the interior. This combination, although ideal for impact absorption, is only really useful for a few collisions before the material is compromised and the helmet cannot provide adequate protection. An alteration to this design would be to use an auxetic material in place of the interior lining. This material displays a negative Poisson's ratio, meaning that it does not behave like a normal material and actually can thicken when subjected to impact, as seen in the right side photos here. This makes them an ideal candidate for blast protection applications or impact, as under compression, the material increases in density and resistance capabilities as it is pulled in from all sides, unlike a normal material, which under a compressive load thins in a direction perpendicular to the force and decreases its resistive capabilities. As a helmet liner, an auxetic material could prevent such onset conditions like temporary blindness due to force on the occipital lobe and possibly allow the helmet to even be used after multiple impacts. Seeking to utilize this amazing property, Dr. Simha has undergone this research project to implement materials and tasked his assistant with creating a virtual head model. Once verified, this model was to be recreated in real life using a ballistic gel torso helmet and 3D printing to simulate impact scenarios in a laboratory setting. Before the model could be created, a variety of literature sources were reviewed to determine the level of detail required for the model. Significant findings from the literature suggest that the level of detail can be minimized on certain parts without compromising the results in order to reduce the computational complexity. For the purposes of this study, as we are interested in the trauma on the interior brain structures, some of these reductions are unreasonable, since structures like the grooves in the brain play an important role in force management and dispersion, yet other structures like the sutures of the skull are insignificant and don't have to be modeled. The literature also recommended that both CT and MRI scans be used together to create an accurate model through a various layer subtraction method. Although ideal, it was challenging to obtain both scans from the same patient, so an MRI scan was solely used as it provides the best image of soft tissues. The workflow for creating a model using image segmentation in a mirror was found by James Hunter in the previous summer's work and altered to suit the needs of the head model. The MRI scan highlights the soft tissue depending on the frequency used to take the images and the density of the tissues, making the brain extremely easy to segment. The brain was mostly segmented using automatic methods and then refined along the boundary layer in order to really create a detailed structure as seen here. The skull and the CSF, however, were very hard to distinguish from another as they were both seen as black structures since high-density objects and fluids are exposed as black in an MRI scan, and thus the skull was roughly segmented first before the CSF and skull were manually separated, as seen here where the skull is seen in green, the CSF has no color, and the brain is blue. After these were all created, they were refined in Amira's using Amira's built-in editing tools and exported to HyperMesh software to create the solid 3D mesh. A tetrahedral mesh was chosen to create the whole model due to the complex geometries of the model. Hexahedral meshes are very difficult to model complex geometries with as they require an increasingly large amount of elements and nodes, which increases the computational complexity, and thus we use tetrahedral elements in order to reduce that. The issue we have with tetrahedral elements is that when modeling an almost incompressible material like the cerebrospinal fluid layer highlighted in yellow here, it might be prone to volumetric locking, so special attention was given in order to prevent this phenomenon from occurring. Before the impact analysis could occur, the material and contact types had to be defined in LS-DYNA. Different literature sources employed different methods and materials, so multiple combinations of each were used using a 6 meter per second sphere impact. In these test simulations, using only a skull model and not including the CSF or the brain, the impact scenario worked very well, although a condition called eroding had to be used in order to prevent penetration issues. These penetration issues were evident in the model of the entire head, including the skull and CSF, where the ball would impact the skull, yet the elements were not eroded from the bottom, and the force was not propagated to the other structures as seen here. Another problem occurred where when the same conditions were attempted to apply from the skull-only model to the brain model, to the CSF brain and skull model, there was not enough memory in order to run any of this, even after 200 gigabytes of RAM was allocated. For future work, it is recommended that the model be recreated in order to increase the detail on the skull and CSF layers. The combination of using a both CT and MRI scan would also help make the scalp and skin layers very simple to subtract and allow the helmet to be fitted to the model as seen in the top photo here, where the helmet was pulled down and pushed back in order to fit properly along the model. By having the skin and scalp model, we'll also be able to improve the detail on the other aspects, including the CSF and skull, and reduce the total size of the model as well in order to make the computational effort less for the computer. If all goes according to plan, this model will be able to be recreated in real life and subject to the pendulum impact tester. That is all. I hope you enjoyed my presentation and can't wait to talk to you all next week sometime. Thank you. Have a very good day.